Hello everybody, this is Chapter 3, Section 1. We're going to talk about the atom, just some of the initial theories and stuff that are involved with the atom. Make sure that you have a periodic table whenever we get to some parts, even a calculator, just so that you can go through a couple of examples with me when we get to them. So starting off, we've got a chemical reaction. You should already have the definition for it back from Chapter 1, so get it down. And then the law of conservation of mass. It's going to sound very similar to the law of conservation of energy, but we are changing out mass and energy. In this case, mass is neither created nor destroyed during ordinary chemical reactions or physical changes. During this school year, we're only going to deal with the ordinary chemical reactions. We will not be discussing nuclear reactions for this particular school year. Again, have your periodic table out. We're going to discuss some things that you're seeing here.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E=mc² equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. The law was revised to become the law of conservation of total mass and energy.
Just going back to some examples that they were looking at there, they did use carbon and oxygen. I'm going to write it down so that under the law of conservation of mass, you can write down this is an example that's going to go along with it, and we'll work it out right over here. So you did have an atom of carbon reacting with 2 atoms of oxygen to give you a molecule of carbon dioxide. So there is 1 carbon and 2 oxygens there for carbon dioxide. That's 3. 1 plus 2 on the left side of the arrow, that's your reactants, is 3. 1 plus 2 on the right side of the arrow is 3 atoms also. If we go look at the law of conservation of mass and look at our mass, right now I'm looking at my periodic table. And I'm going to find carbon and oxygen that we have over here. So if I look at carbon, you can tell carbon has a mass of 12.01, so as I hover over it, it's 12.01. Oxygen is 15.99, so we're just going to say 12 for carbon, 16 for oxygen, and go work out our example. So over here again, we've got carbon plus 2 oxygen yields carbon dioxide. So the mass of carbon was 12. The mass of oxygen was 16, but since we have 2 of those, 2 times 16 is 32. Based on the law of conservation of mass, if you have, it doesn't matter what mass unit you're working with, we're just going to go hypothetical grams, 12 and 32 grams of each of those, you would expect a total of 44 grams of oxygen. So again, we are not creating or destroying any mass along the way for this ordinary chemical reaction. Moving on, we have 2 more definitions for you. We are going to look at the law of definite proportions and the law of multiple proportions. I'll give you examples of both of these 2. Get these definitions in your notes. But if I just go back and I look at the word definite real quick, if I asked you to define definite, I'm hoping that you are coming up with something that is related to fixed, always, it's set. Be thinking of that as you go through this, and then multiple is going to obviously mean many. Please get those definitions.
Table salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from.
So again, as we look at this, you should be familiar with sodium chloride, the formula, NaCl. Yes, there's just one atom of each within that structure, but if you look at the mass of sodium and the mass of chlorine, and we'll do some math here momentarily, the mass of each of those, the percentages are given are based out of 100%.
The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
So let's do just a little bit of math. Again, we're talking about sodium and chlorine. I'm going to go back up to my periodic table so that we know what we're looking like. Hovering over sodium, and I'm going to try to keep the math simple here. But sodium, we're going to use, instead of 22.99, we're going to use 23. And then for chlorine, the mass is 35.45. I'll go ahead and use that number. And we'll head back over here to our example. So sodium, the mass was roughly 23. For chlorine, 35.45. If you add those two numbers together, you get 58.45. Adding up those top two numbers. If you divide those respectively the way I have it written up and then multiply by 100 to get yourself to a percentage, then you're going to come up with 39.35% and 60.65%. Again, those percentages look a lot like these numbers that kept popping up over and over and over again. And you know that I didn't use all the decimal places that were on the periodic table, but those values, that's how they get the percent by mass for a compound. So again, sodium chloride is a 1-to-1 ratio of atoms, but the masses of each of those atoms is different. So this is the law of definite proportions. And just like their sample said, I can take some table salt, I can pour a little bit in my hand. 39% is sodium, 61% is chlorine. I can fill up my entire classroom with table salt. 39% of it's sodium and 61% of it's chlorine by mass. So that's the law of definite proportions. The proportions do not change based on the sample size you are working with. Moving on to the law of multiple proportions. So in this one, we're going to be looking at a couple of elements that can be arranged multiple ways to create different compounds. So the same elements will have a different arrangement to create different compounds.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with the fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using two compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these two compounds is 8:16, or 1:2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we have the same relative amount of hydrogen.
Okay, so again, she was talking about the fall point that you've got there at the end of this particular law, but I am going to simplify it into what she was stating. If you are using the elements hydrogen and oxygen to make up these two compounds, you have respectively it looks like the same amount of hydrogen in each one, but you can tell in the second example there's twice as much oxygen. And when you look at those numbers over here, based on mass, that is also true. So the same two elements, the ratio is different, and you get two different compounds. So same elements used multiple ways. Another example I know that you're familiar with is going to be carbon and oxygen. So if I just have 1 and 1, that's carbon monoxide, typically given off by your car. And then carbon dioxide given off by us. Both of them contain carbon and oxygen, but again, the ratio is going to be different. We're going to highlight just a few more examples. In the top one, you've got water. It's looking at the actual masses that you have for each of them. I mean, those values are very small. But if you add up the two on the left, your reactant values, it equals the mass of the product. The same goes with sulfur dioxide in the middle, and then the chlorine molecule, or it's really phosphorus pentachloride that's broken down into two different products at the very bottom. So again, law of conservation of mass, they're giving you the specific values in kilograms for those atoms, and we are not creating or destroying mass along the way. And in this one for law of multiple proportions, this time they're using nitrogen and oxygen as their examples. Again, same two elements, the ratio is a little different. You create two different compounds, and it gives you the description of each of those as far as, well, what is reactively, the difference between nitrogen monoxide and nitrogen dioxide, and it gives you that information. So again, there's your mass ratio there. Multiple proportions, there's multiple ways to put nitrogen and oxygen together, and those are not the only two compounds. Moving on to Dalton's atomic theory. So I've given you a few laws. These laws are going to be used within Dalton's atomic theory. Dalton's atomic theory, there are 5 parts to his theory. You need to make sure you write down all 5 parts. The very first person, I guess you could ever think to have an idea of all of this, what are atoms made of, is going to be Democritus. Democritus happened back about 400 BC, and then Dalton here in the early 1800s has come along and is like, okay, I know about these 3 laws that we have now. I'm going to try to come up with the first official theory for atoms and get all 5 parts written down. Here are the first 3, and we'll go over each of those, and I will also give you a little bit of information about them too as far as how they've changed. So the first one, all matter is composed of extremely small particles called atoms. I'd put a check mark beside that because that still holds true today for what we look at. Number 2, Dalton says atoms of a given element are identical in size, mass, and other properties. Atoms of a different element are different in size, mass, and other properties. So he's saying all the atoms of oxygen are identical, but they will be different to all of the atoms of hydrogen, or oxygen is different from nitrogen, and so on. So that second part is true, but since Dalton's time, and we'll get into more of this a little bit later on, I'm going to put a big X here on this top part because it says atoms of a given element are identical in size, mass, and other properties. We now know that most elements, that does not hold true, and it's because of isotopes. You've probably heard that word before, but we will talk more about isotopes a little bit later. But for instance, carbon, we know that not all atoms of carbon are identical. There's carbon 12, carbon 13, carbon 14. One of those is typical carbon, like you have in living materials, people, things like that. But carbon 14 is going to be used for carbon dating, which is a radioactive version of carbon. Again, we'll get into some more of that a little bit later. Number 3, atoms cannot be subdivided, created, or destroyed. Again, early 1800s, that is what they thought. That was their best theory at the time. But we now know that that is not true. We know we can subdivide atoms now. You've heard of the electron, the proton, the neutron. It goes even smaller than that, but we will concentrate on those subatomic particles a little bit later. So atoms can be subdivided. Again, keep up with Dalton's theory. Keep up with each part to his theory. There's 5 parts, and if I make any changes, make note of those too. And the 4th and 5th part of Dalton's atomic theory, part number 4, atoms of different elements combine in a simple whole number ratio to form chemical compounds. We've been showing you that. We've been showing you that with the law of multiple proportions. Carbon and oxygen, yep, they can make carbon monoxide, carbon dioxide. Hydrogen and oxygen, you've got your water, you have your hydrogen peroxide, and the list goes on and on. So yes, that is still true. And then number 5, in chemical reactions, atoms are combined, separated, or rearranged. Absolutely still true. And just I've already highlighted a couple for you, but here's another one. For water, you've got 2 hydrogen. Again, I'm being very simple. With 1 oxygen is going to give you a molecule of water. They are combining, and that is a chemical reaction. So to round out section number 1, not all aspects of Dalton's theory have been proven to be correct. I've already highlighted for you, yep, atoms are divisible. Protons, neutrons, electrons. And it says a given element can have different masses. That's when I was talking about isotopes. And then the unchanged parts, yes, this part right here, they are still unchanged. I will see you next class.